Alright, welcome to another episode of Math with Haas. So this is Precalculus, we're in season 1, so that's exponentials and logarithms, and this is our 4th video. Now, we last time introduced the concept of Euler's number. Euler's number we discovered by using actually the compound interest formula with specific values, and we found that Euler's number was approximately 2.718. And now, what is Euler's number really? We discovered it, sure, but what is it used for? And the claim is that Euler's number allows us to model continuous change. So when we talked about the compound interest formula, we had A is equal to the initial amount times 1 plus interest rate over number of times compounded raised to the number of times compounded times time. If we want to consider now continuous change, that means every single moment, every single day, over the whole year, interest is being compounded. We can use Euler's number. So, our equation for continuous change will still have our initial amount, but all of this here gets condensed, pretty much, and we're just left with e to the RT. So this whole term here is now condensed to the amount initially invested times Euler's number to the interest rate times time power. Now, some of you might be a little skeptical about this. There's actually some calculus involved behind this, so we'll have to wait to justify our claims for that until then. So the claim is, by using a little bit of calculus, that we can demonstrate that the model continuous changes, we can use Euler's number in this fashion. And so for compound interest or like radioactive decay, if we want to think those quantities as continuously changing, especially with radioactive decay, that should make sense, since it's not like it's radioactive decay at one moment, then it stops for a while, then it starts again. No, it's at every single moment, seamless over time, that the material is degrading radioactively. So Euler's number allows us to model that behavior. So let's go ahead and look at an example. So this is an example of radioactive decay. So let's go ahead and type this out. So we have, how about radon 222? We know it decays at a continuous rate of 17.3% per day. Let's say we have 200 milligrams. How much of 200 milligrams will remain after, how about 2 days? See what happens after 2 days. Alright. So, how much of this will remain after 2 days? So let's go ahead and figure out information. So keep in mind, this term here, radon hyphen 222, that just tells you the particular isotope of radon. This 222 has nothing to do with math formulas, computations. We just ignore it. In fact, let's ignore it right now. Get rid of that. This radon stuff decays at a continuous rate of 17.3% per day. We probably just broke some scientist's heart here. So continuous, that means we have to use this formula right here. Alright, 17.3% per day. So this is our R right there. And Well, actually, we can use this magical one right here. Ooh. So that right there is our t. Okay. That is just magical. Alright, back to math. So let's separate quotient. Y is equal to... Ooh, we forgot to talk about that. New color. How about this one? So we have that right there. How much of 200 milligrams? That has to be our A. Alright, so we have 200 milligrams of... Well, that's our radon. Has to be E to the 0.173 times 2. So we have 17.3% interest. Don't forget that decimal goes back 2 places because it's a percent. Alright, so now let's calculate this value. 200 times e to the 0.173 times 2. What did we forget here? We made a mistake. How can something decay grow by 83 milligrams? That's funny. So, pro tip. Decays. That tells you that R is negative. Do not forget the negative sign right there. Let's put a big old negative. Alright. Now, good news is, if you have a calculator like this one, we can just hit, we'll use the up arrow, then we hit enter, and now we can go over and edit it. So I'm going to hit second, and then this button for insert. Let's put a negative in there. Perfect. Enter. There we go. Alright, so let's go back to blank. So we will have about 141.5 milligrams after 2 days. So about almost 60 milligrams decay. Alright. So that is an example with radioactive decay. Alright. Let's think of another example. Let's go ahead and go back to finances. So example, here we go, there's our text box. Suppose you invest about $4,500 into a bank account, compounded continuously for 7 years at a rate of, let's be generous, 3.14%. How much is your account worth? Let's change it. How much is your account worth? Alright. Math time. So we want to look at this. That 4,500 is our A. Alright, so we keep reading. Compounded interest, or continuously compounded. So since it's continuously compounded, that tells you you have to use this formula. Y equals A e to the RT. And then 7 years, that tells you time is equal to 7. Now, this right here, that 3.14, that is equal to, well, that's percent, that's equal to R. Okay, maybe I should quit using that. That doesn't look good. Though it does look spectacularly magical. Alright, so Y is equal to 4,500 E to the 0.0314 times 7. Alright, 4,500 times E to the 0.0314 times 7. Alright, so we made $1,100. So Y will equal 5,606 and 22 cents. Boom. Alright. So, let's see. I think we'll call that good for now. So, thank you for joining this episode of Math with Haas. When we get together next time, we will look at what does the graph of these functions even look like. I mean, we've talked about exponential functions for a few episodes now, but we haven't even looked at their graphs yet. It's time we do. So, if you've enjoyed our content, please subscribe to his YouTube channel, support us on Patreon. I will see you next time. Thank you for joining our math party. Alright.